Good afternoon, students. In the previous video, I have discussed the self-inductance in the solenoid, and therefore after that I have give a brief idea about the mutual inductance. Today I will continue with this mutual inductance part. Okay, so let us continue. So what is mutual inductance? Suppose a coil is here and it is being connected with the battery, and another coil is also here, and here a galvanometer is being connected. Okay, so suppose this is called the primary coil and this is the secondary coil. Okay, so when this primary coil is being connected with the battery and suppose a key is being connected here, if this key is on, then the momentary deflection of galvanometer is being produced. Why this is produced? Because as we pressed the key or as we completed the circuit within this coil or within this primary coil, then a magnetic field is being produced here, and as the magnetic field is produced, some line of magnetic flux passes through this secondary coil as well. Okay, so as we more and more increase the pressing of this key, suppose I have connected here with the rheostat. A rheostat is there. Okay, so as we increase the resistance, so the magnetic flux that is passing through this primary coil also hit the secondary coil. So as the magnetic flux or magnetic lines of force here in the primary coil increases, the secondary coil it is also being increases. That's why the galvanometer starts to deflect. Okay, so therefore due to the change of the number of flux lines, the magnetic flux basically and EMF is also induced in that secondary coil, and therefore as the EMF is produced here, so what is the first thing is that as we are increasing or we have completed the circuit in the primary coil, then a magnetic lines of or magnetic field is being produced. As the magnetic field is being produced here, so a magnetic lines of force is also produced. As the magnetic lines of force is producing in this primary coil and the secondary coil is near the primary coil, so therefore this magnetic lines of force also influence this secondary coil as well. As the secondary coil is being affected by this magnetic flux, so an induced EMF is also produced in this secondary coil, and as the induced EMF is produced here, so a small amount of current also flowing through this coil. Okay, and why this current is flowing? Because according to the Lenz's law, we all know this, that if a current is producing in a coil, it always tries to reduce the effect or reduce the cause of the current it is producing. Okay, so therefore the current is producing due to the induced EMF in the secondary coil. Okay, so this concept is called the mutual inductance. Okay, so what do you mean by the coefficient of mutual inductance? Now suppose if I1 be the amount of current in the primary coil, and due to this current a magnetic flux linked with the each turn of the secondary coil is phi 2, and if N2 be the number of turns in the secondary coil, so number of flux linkage in the coil will be basically N2 phi 2. So, these N2 phi 2s, that is the number of flux linkage, will be directly proportional to I1. So, amount of flux linked with the secondary coil, that should be equal to the amount of current flowing in the primary coil. So, therefore, this reaction or this equation becomes M of I1. What is this M? This M is known as the coefficient of mutual inductance. So, what will be the value of this M? So, value of this M will become N2 phi 2 by I1. Okay. Now, if I consider I1 equal to 1, then M will become basically N2 phi 2. So, from this, what we can conclude? We can conclude that coefficient of mutual inductance of two coils is equal to the number of magnetic flux linkage of one coil, that is the secondary coil, when a unit current flows in the primary coil. Okay. So, what will be the change? If on changing the current in the primary coil, the EMF induced in the secondary coil will becomes E2. As in the primary coil the current is being changed, then also the induced EMF in the secondary coil also be changed, right? And the change is defined as the E2 here. Okay. So, this E2 will basically, according to the Faraday's law, N2 will be d phi 2 dt. What is phi? Phi is nothing but N2 phi 2. Clear? So, I consider it as delta by del t. And what is this N2 phi 2? Previously we know this, it is nothing but the M. So, E2 will be basically minus M, change M of I1 by delta t. Okay. So, this is the relation between the EMF, mutual inductance and current. Okay. And what is the unit of this? The unit of this mutual inductance is defined as Henry H. Okay. Which is basically the volt per ampere per second. So, 1 Henry equals to basically 1 volt by 1 ampere per second. Hopefully, it is clear to all. So, next is that eddy current. What is eddy current? What is eddy current? Eddy current is defined as the induced current in the body due to the changing of magnetic flux. Okay. This is also known as flocculent current and its name because of the scientist flocculent. Okay. So, basically this is also known as the eddy current because they have the pattern of addition of water. So, let us discuss this eddy current in an elaborate way. So, if we consider an electromagnet, suppose an electromagnet is there. And it is being connected with the battery. Okay. So, the current that is formed in the eddy current, mathematically if we say that for the eddy current, mathematically what we can say that it is basically I equals to minus d phi dt into 1 by R. So, this is the mathematical format of the eddy current. Okay. So, what is the example of eddy current? For the example of eddy current, basically for the metal plate, in absence of the magnetic field, there will be no damping and if magnetic field is present here, then the damping will exist. So this is due to the presence of the eddy current. Okay, so this is the small thing or small part of your syllabus, that is the eddy current. Okay, hopefully it is clear to all, and by this video the electromagnetic induction part is completed. Okay, thank you.